Hello, I'm Gavin Lowe. I'm a tutor at St Catherine's College, Oxford. What I'm going to do today is talk about the topic of graph search, and in particular how we can use this to solve various types of puzzles. So first of all, what's a graph? Well, here's a picture of a graph. A graph's a mathematical object containing nodes. So these things in the sort of rounded boxes, they're nodes, and edges connecting the nodes. So each of these, that's an edge here connecting node 6 to node 8. In the particular case we're going to be considering, one of the nodes is a start node, in this case node 0. So in the pictures I'm going to represent the start node with an edge coming in from nowhere like there. And some of the nodes are going to be target nodes, here the nodes in red. What we're interested in doing is finding a shortest path from the start node to a target node. So in this case the shortest path is the path 0, 1, 4, 7, 12. That's certainly a path from the start node to a target node, and it turns out to be the shortest path. Why is this interesting? Well, it can be useful for various different problems. So we're going to look at a few puzzles that you can solve in particular using this idea of graph search. So here's a puzzle you've probably seen before. It's the puzzle concerning the wolf, the goat, and the cabbage. The scenario is that a man has to take a wolf, a goat, and a cabbage across a river. Don't ask why. He's got a boat, but the boat's only big enough for himself and one out of the wolf, the goat, and the cabbage. So we can ferry one object across at a time. However, if he leaves the wolf and the goat alone together, the wolf will eat the goat. And likewise, if he leaves the goat and the cabbage alone together, the goat will eat the cabbage. Not good. So the question is, how can he do this? How can he ferry each of the three objects across the river? Well, we can solve this by building a graph model of this puzzle. So each node in this graph is going to be a 4-tuple representing the location of the man, the wolf, the goat, and the cabbage. So here's a picture of that graph. It's quite a small graph, it's got about 15 nodes. The start node up here, each of them is on the left bank, represented by the L there. And from that start state, there are various moves that are possible. Well, one possibility is that the man goes across the river on his own, in which case we get into this state where he's on the right bank, but the wolf, goat, and cabbage are still on the left bank. Well, that's not good, because either the wolf will eat the goat or the goat will eat the cabbage. That's an unsafe state. In this picture, I've just drawn the unsafe states in black, just to help understand what you can do. Alternatively, the man could go across the river with the wolf, in which case we get into the state where he and the wolf are on the right, and the goat and the cabbage are on the left. But again, that's an unsafe state. There's another unsafe state here. The one safe move he can make is he could go across the river with the goat, in which case he and the goat on the right bank, and the wolf and the cabbage on the left bank. So there's an edge between those, and that's another safe state. From this state, well, one possibility is he rows back across the river, taking the goat with him, in which case we're back into the start state. That's not very useful, but it's a legal move. Or more usefully, what he could go is back across the river, leaving the goat behind, in which case we're into this state here. The man, the wolf, and the cabbage are on the left, and the goat is on the right. And then so on, and you can stare at this picture in your own time if you want to check I've done it right. The target node that we're aiming for is down here, where all four of them are on the right bank. Having drawn this graph out, we can see that there are actually two shortest solutions, either following the path down here or following the path down here. Okay, so this puzzle's small enough that you can actually just enumerate all the states fairly easily. However, we're interested in searching much bigger puzzles, much bigger graphs than this. Here's another example puzzle. So this is a puzzle that Lewis Carroll came up with. The idea is to find a path of words. Each word differs from the previous word but in precisely one letter, and these are linking two given words. So the example that Lewis Carroll came up with was a path linking grass to green, and he gave this solution grass, crass, cress, tress, trees, freeze, freed, greed, green. Each word differs from the previous in one letter. Turns out there are actually shorter solutions than that one. Well, we can build a corresponding graph model where, again, the solution to this puzzle is the shortest path in the graph. In this graph model, each node is a word, and two nodes are linked if they differ by a single letter. So I've drawn part of the graph here. The whole graph would have as many words as there are in your dictionary. It's going to be too big, but this is a big enough part to understand. So, for example, the word grass has edges to glass, crass, grass, trass, and a few others I haven't drawn. The solution that Lewis Carroll came up with is the path along here. In fact, there's a shorter solution: grass, trass, tress, trees, treed, greed, green. So when you can see the relevant part of the graph, it's obvious. But what we want to do is come up with a program for building this graph and searching it to find a shortest path. Here's another application of graph search. This isn't a puzzle, it's in the area of verification. I thought I'd put this in. It's the area of computer science that I do my research in. The idea of verification is that we've got some computer program that we want to verify. And what we'll often do to verify this program is build a graph model. Every node in the graph is a state that the program can get into, and that each edge in the graph corresponds to a step of the program. What we then do is identify certain states as being bad, states where things have gone wrong, and what we want to do is search the graph looking for a path that leads to a bad state. Well, we actually hope there's no such path that leads to a bad state. If that's the case, the program works correctly, it never gets into a bad state. But by searching the graph, we can verify that fact. Here's a more concrete example called mutual exclusion. So this is a problem from parallel computing. Suppose we've got two parallel programs or parallel processes that share a resource. This resource might be a printer or an area of memory. The important thing is that at most one process uses this resource at a time. You can imagine if two processes try to use a printer at the same time, they might interfere. Likewise, if they try and use the same area of memory at the same time, they might interfere with one another. So we want at most one process using the resource at a time. This is called mutual exclusion. Here's an algorithm known as Peterson's algorithm that solves this problem, and we can see how to solve this using a graph search. So I've written the algorithm out in some sort of pseudocode. This algorithm uses three variables: flag 0, flag 1, and turn. The flag variables are used to indicate that a particular process is trying to access the resource, and turn is sort of used to mediate when they're both trying. Here's the code for process 1 over here. Process 0. Process 0 starts by setting its flag 0, to be true, to indicate that it's trying to access the resource. And it sets the variable turn to be 1, to indicate that the other process should have priority. It then has a loop. So while flag 1 is true, in other words, the other process is trying to access the resource, and this is and, turn is 1, it does nothing. So it will just loop around here, repeatedly testing whether flag 1 is true and turn is 1. If so, go back around the loop and try again. So it keeps looping until that condition is false. When that condition is false, it can then use the resource, and when it's finished with the resource, it sets flag 0 back to be false. Process 1 is very similar, except it uses flags the other way round and sets turn to be 0 rather than 1. Okay, so symmetric. These two processes execute independently, and they might run at different speeds. So the question then is there some way of these two processes executing, some funny interleaving of steps that actually leads to both processes using the resource at the same time, both being at line 4 of their program at the same time? Turns out the answer is that that can't happen, that it does ensure mutual exclusion, and you might stare at the code and persuade yourself that that's true, But we want something a bit more of a persuasive argument than that. We can do that by building a graph model of this scenario. So what we can do is build a graph model for Peterson's algorithm. Each node is going to be labelled with a 5-tuple, 5 bits of information. The line number for process 0, the value of flag 0, either true or false, the line number for process 1, the value of flag 1, and the value of the turn variable, either 0 or 1. So there's finitely many states. The bad states that we hope we can never get to are those states where both processes are at line 4. And we hope to find that there's no path leading to a bad state. Here's part of the graph model. I started drawing it and found that the slide wasn't big enough, but we can at least explain some of the ideas on this. Don't stare at this too hard. You might spot my errors. The initial state up here, both processes are at line 1. Both the flags are false, that's the initial state, and the turn variable is 0. One possibility is that process 0 takes a step first. I've labelled the edges with the identity of the process doing a step. Well, if you remember the code, it then goes to line 2, it sets its flag to be true, but the other values of the tuple are all the same as previously. Alternatively, process 1 might take a step initially and lead to that state. You can see that there are some confluent paths. For example, if 0 takes a step and then 1 takes a step, you get to the same place as if 1 took a step and then 0 took a step. Okay, and you can build the graph up like that in principle, but it's hard work and it's tedious. What we want to find out is whether there's any path that leads to a bad state, i.e. a state where both of the processes are at line 4. Okay, so we've reduced the problem of verifying Peterson's algorithm to a graph search problem. Okay, each of these problems can be solved by graph search. So what we're going to do is see an algorithm for graph search, for finding the shortest path in a graph. If we can do that, we can then solve all these problems and many other problems that can be cast as a graph search problem. So we want to have a way of representing a graph as a software object so we can operate upon that. So I'm going to be presenting a bit of code. I'm using Scala to present the code because it's the language we use for quite a lot of our courses in Oxford. It's my favourite programming language. It's a nice language when you get used to it. But don't worry if you don't understand every step of the code. So a graph is going to be an object of this trait. A trait in Scala is just a way of describing the interface of an object without describing precisely how it works. It describes what it does rather than how it does it. So a graph is going to be a thing that provides these three functions. In particular, the graph is going to be parameterized by the type of nodes. So throughout this, capital N is going to represent the type of nodes. We've seen different graphs with different types of nodes. So for our purposes, a graph is going to be something that, first of all, has an initial node. So init is just going to give the initial node of the graph. It's going to be a node of type n. It's going to have a function sucks that gives the successors of a particular node n. So this just means it's a function that takes a node little n and gives you back a list of nodes, a list of big N's. And finally, it's going to have a function that tests whether a particular node is a target node. So this is a function that takes a node little n and gives you back a Boolean, true or false. Okay, so that describes what a graph is, but then we can define particular graphs for these different graph search problems. So I'm going to give you the implementation of the graph for the wolf, goat, cabbage problem, and then sketch the word search problem, but you can build other graphs in a similar way. So for the wolf, goat, cabbage problem, remember we represented each node by a 4-tuple like that, representing the locations of the man, the wolf, the goat, and the cabbage. Well, in the implementation, it's easiest to use Booleans, true and false. False is going to represent the starting bank, and true is going to represent the target bank. Okay, so here's an object that represents the it's called WGC graph. It's the wolf, goat, cabbage problem graph, and it's a graph where all the nodes are 4 tuples of booleans. The initial node of the graph is where all 4 of them are on the starting bank, so that's the 4 tuple where all the entries are false. A particular node is the target node. Well, let's just unpack the node as a 4 tuple MWGC. Well, that's a target node if each of these is true. So if M is true and W is true and G is true and C is true. Okay, so that's easy to test whether a node is a target node. The successors of a particular node, it's going to take a little bit more work, but here's the code for that. It's useful to have a helper function, isSafe, that tests whether a particular node is safe, a particular state is safe, i.e. the wolf can't eat the goat and the goat can't eat the cabbage. So given the positions of the 4 objects, I reckon this complicated looking Boolean expression here captures whether or not it's safe. So first of all, this state is safe if the man is on the same bank as the goat. Well, in that case, he can stop the goat eating the cabbage or the wolf eating the goat. Or, the wolf is on a different side from the goat, so the wolf can't eat the goat, and the goat is on a different side from the cabbage, so the goat can't eat the cabbage. Okay, it takes a little bit of staring at, but I reckon that captures the fact that that particular state is safe. Here's a function that gives the successor states of a particular state. So again, if we unpack the node as a 4 tuple MWGC, and start by testing whether this is a safe node. If it is, what I'm going to do is build a list which we'll call result, which will end up containing all the safe successor states, all the successor states. Well, one successor state is certainly where the man rows across on his own, in which case the man will be on the opposite bank from what he was on previously, which we can write as like this. The exclamation mark is not. So if M was true, that's false, and if M was false, that's true. So that just flips the sense of M. So that's the bank, that's the state that's the same as the previous state, but where the man has changed bank. Alternatively, it might be possible for the man to row across, taking the wolf with him. Well, if in this starting state the man is on the same bank as the wolf, he could row across, taking the wolf with him, in which case the man and the wolf are now on the opposite bank, but the goat and the cabbage are where they were previously. So that's the new state. This thing here just adds that tuple onto the end of this list result. So we add this tuple onto the end of result. And likewise, if the man's on the same bank as the goat, he could row across, taking the goat to get to that state. So we add that to the result, and then do a similar thing with the cabbage, and return that list at the end. So we build up the list of possible successor states in this variable and return at the end. Alternatively, if the state is not safe, we come down here. Well, in this case, we failed. We return the empty list of successors. We've gone wrong at some point. Okay, so that's defined a graph for the wolf, goat, cabbage problem. I'm now just going to sketch how we can do a similar job of building a graph object corresponding to the word search problem, the word path problem. The most interesting bit there is calculating the successors of a particular word W. Well, we need to assume here that we've got access to some sort of online dictionary. I'm going to assume that we've got some sort of file containing, a dictionary file containing a list of all legal words. So suppose we want to contain the successors of a particular word W. Well, we can start by iterating through all the characters of W in turn and considering each string formed by replacing that character with a new character. So let's call that string W1. We consider all strings W1 formed by replacing a particular character with a different character. We can then test whether W1 is a legal word, whether it's in our appropriate dictionary file, and if so, include it in that list of successors. So we can just iterate through building up the list of successors of a particular word. So we can build a graph of the word path problem in a similar way. Okay, so given a graph describing the particular problem we're interested in, the next problem, we're going to actually think about how to search in this graph. So I'm now going to write a generic search function that takes an arbitrary graph which I'm going to call G. So this is a graph where the nodes are of some type n, and it's going to aim to return the shortest path to a success state, a target state. However, it's possible that there's no reachable target state, in which case we need to return some special value. Well, the standard way of doing this in Scala is to use what's known as the option type. So if the search succeeds and finds a particular path, a list of nodes leading to a target state, it's going to return a value of this form, some path. So this is just path wrapped up inside a sum wrapper, indicating that it was a success. Alternatively, if the search fails and doesn't find any reachable target node, then it's going to return a special value, none. So we either return a sum path or a none. There's a type, option list n in Scala is the union of these. All values of that type where path is a list of n's plus the special value node. So my search function is going to return something of that type. Here's the idea of this graph search algorithm. It's an algorithm known as breadth-first search. So what we do is start with the initial node. We then consider all the nodes that are one step away from the initial node. We then consider all the nodes that are 2 steps away from the initial node, and so on. So for each node that we get to in this order, we test whether it's a target node. If so, we're done and we return and finish. Otherwise, we need to calculate the successor nodes because we'll consider those on the next round. So that's the basic idea, but we need a bit of bookkeeping. We need to keep track of the nodes that we still need to deal with. To do this, I'm going to use a queue. So a queue is a standard computer science data type. It basically contains a collection of values, in this case, a collection of nodes, and it stores them in queue order. So in other words, you can add things to the end of the queue and take things off from the front of the queue. So we can store the nodes that we still need to search in this queue. Well, actually, I'm not just going to store nodes. I'm going to store pairs like this. I'm going to store a node, but pair that up with the path that leads to that particular node. Because at the end, if we do find a target node, we want to have access to the path that got there. So we store each node together with the path that leads to it from the start node. Okay, and this is an algorithm called breadth-first search. Oops. Sorry about that. Okay, here's the first attempt at the breadth-first search algorithm. This sort of works, but not very well. I'll come back and improve it in a moment. So we're searching in the graph G. What we need to do is have a queue that stores the nodes that we still need to consider together with the path that led to them. And we start by adding to this queue the initial node. Remember, that's g.init. That's how you extract the initial node from G. And the path that leads to it, well, that's the list of nodes containing just that node. It's a singleton path. Okay, and this adds that value to the queue. Most of the work is done inside this loop here. So while the queue is non-empty, so while there's still more things in the queue that we need to deal with, we dequeue an element from the queue. We just take the element at the front of the queue, and let's call that n path. So this is a node n that we encountered earlier, and path is the path leading to it. We then need to consider all the successor nodes of that. So this for loop considers each element of g.sucks n. Remember, that's the successors of the node n in this graph, and this considers each node from that in turn, and in turn calls each of them n1. So n1 is one of the successors of n. It tests whether n1 is the target node. Remember, that's the isTarget function on the graph. If it is, we're done. We found a path to a target node, so we just need to return that. Well, path was a path that led to n, and in one step you can then get from n to n1, so the complete path is path followed by n1. And remember, we wrap that up inside a sum wrapper to indicate we successfully found a path. If it's not a target node, we need to consider onwards from n1. So we enqueue n1 into the queue. We add n1 together with the path that leads to n1. And then we can do that for each successor n1 of g, and then we go on to the next node in the queue. If we get to the state where the queue is empty, that means that we'll have considered every reachable node on the graph and not found any target node. In that case, there's no path to a target node, so we end up returning the special value none to indicate that. Okay, so that will basically search the graph. It sort of works, but it doesn't work well in practice. So let me just point out some ways in which it will sometimes work poorly. Basically, it does a lot of redundant searching. It repeats work. Anytime you repeat work, that's going to be inefficient. Let's think about the word path problem as an example. Well, it will consider paths like grass, crass, grass. There's an edge from grass to crass. There's an edge from crass to grass. So it would certainly consider that path, but that's not a very sensible path to consider because we got back to where we started from, back to a node that we considered earlier. Likewise, it will consider paths like this, grass, grass, crass, but that's not very useful because there's a shorter path just going from grass directly to crass. So any path that starts with this, there's going to be a shorter one that starts without the grass in the middle. So that's never going to lead to a shorter path, in particular because we'll have found crass after a single step. We'll have found crass with a path up here like that. So in that case, we've got, after 2 steps, to a node that we actually encountered earlier on in the search. Here's a worse way it might go wrong. Suppose the graph has no reachable target node, but there's a loop in the graph. This is true for the verification problem, the Peterson's algorithm that we looked at. There's no target node, there's no bad node, but actually there's a loop. In that case, this search will consider longer and longer paths going round and round the loop more and more times, and so will never terminate. That's not good. We can solve all of these problems very simply. The solution is to keep track of the nodes that we've seen so far, and if we find a node that we've seen previously, we know we've already dealt with this node, we don't need to search on from that node again. So here's the improved algorithm, and this is about 90% the same as before, so I'm just going to concentrate on the differences. Again, we have the queue storing the nodes that we still need to deal with, but in addition, we store the set of nodes that we've seen so far. So Scala collection mutable set, it's an implementation of a set inside the Scala library, so we can create a set of nodes. And let's just call this scene. So it's going to be the set of nodes that we've seen so far, and we start by adding the initial node to it. And we initialize the queue in the same way as before with the initial node and the path leading to it. The main loop is much as before. Again, while the queue's not empty, we remove a particular node and its path from the queue, we iterate through all the successors. If the successor is a target node, we found a target node, we return the path to it. Otherwise, here's where it's slightly different. We start by testing whether scene contains n1. If scene does contain n1, we shouldn't search onwards from n1 with this path, because we're searching from n1 via a different path. We'd be repeating work. So if scene does contain n1, we do nothing. We forget about n1. However, if it's not the case that scene contains n1, we do continue searching from there. So we add n1 into the queue together with the path, but we also add 1 into the scene set to record that we have now seen n1 for the first time. So if we get back to this by another node, we won't search onwards from that node, from that instance. We're only searching on from this instance. Okay, so that avoids repeated work, only searches on from each node once, and in particular, if there's no reachable target node, and assuming the graph is finite, eventually we'll get into a state where the queue is empty and we'll drop out and return none at that point. Okay, so that's the graph search algorithm, and we can apply this to each of the 3 examples we saw earlier and solve the 2 puzzles using it, or show that Peterson's algorithm is correct, never gets into a bad state. Okay, so here's a summary. Many interesting problems can be cast as graph search problems. It's often useful to have this mathematical abstraction down to a more mathematical object like a graph. They're often easier to think about and program around, but also this abstraction gives greater generality. Rather than having to write a separate program for each of these different puzzles and for the verification problem, we can basically concentrating on writing the graph search algorithm and then employ that graph search algorithm to solve each of these different problems. And in particular, I've told you a little bit about breadth first search. What I want to do is just finish by pointing out a few links to some of the lecture courses that we teach here in Oxford. Breadth first search crops up in a number of courses, including the 5 that I've listed here. So the first one on my list there is imperative programming. This is our main first year programming course. That course studies very many different aspects of programming and in particular ways of reasoning about programs and coming up with correct programs. But one of the examples in that course is this idea of graph search in order to solve these puzzles. Actually, I took the two puzzles from the last time that I taught the course to put them into this talk. The second course on that list, Design and Analysis of Algorithms, that's again a first year course. That looks more at the idea behind algorithms, concentrates on techniques for proving algorithms correct, looks at different classes of algorithms, and looks at the complexity, the efficiency of algorithms. So it studies breadth first search and other algorithms from a more theoretical point of view. Artificial intelligence is a second year course. Well, it turns out that many problems in artificial intelligence are really search problems and can be cast as a graph search problem. Often you've got a set of potential solutions and you want to search for that. Well, you can cast that as a graph and searching in a graph. One part of AI is solving puzzles. I've shown you examples of that. The artificial intelligence course also looks at different graph search algorithms. Some are better in different scenarios, and in particular describes some graph search algorithms that are somewhat more targeted. The algorithm that I've shown today was slightly untargeted, just searched the graph in all directions without taking any thought about what's the better direction. Sometimes it's possible to come up with some tactics that target in a particular way. For example, in the word search problem, it seems better to search from words that are closer to the target word, have more letters in common with the target word. Well, there's a search algorithm called A* that uses that idea. Okay, so AI course looks at various different search algorithms, including this breadth first search. The next course on the list there is concurrent programming. Concurrent programming, parallel programming is the same thing, basically. Often we want to look at really big graphs and search really big graphs. In my work on verification, I'm often doing verification searches, where I'm looking at graphs with billions, tens of billions, hundreds of billions of states. That takes a long time. When you're looking at a graph that big, it's useful to write a parallel program so you can search different parts of the graph in parallel, have many parallel processes working together to do that search. One of the examples I put into the concurrent programming course is this idea of breadth first search. How can you implement breadth first search as a parallel algorithm so that different parallel processes cooperate together to do the search without interfering with one another? And the final course I've highlighted there is computer-aided form of verification. So that's picking up on the idea of verification again, verifying a program or computer system. In that course, you see various different techniques for doing that verification, but a lot of them come down to graph search. Okay, so what I hope I've persuaded you in this talk is that graph search is an interesting problem. You can use it to solve many interesting problems like solving puzzles, verifying programs, and so on. And actually, you can encapsulate all of these different types of graph search or different instances of graph search into a single algorithm. Okay, goodbye.